Hi, my name is Saeed Amizadeh. This is a joint work between Microsoft and Microsoft Research AI. In this work, we propose a neuro-symbolic framework based on first-order logic to disentangle perception and reasoning in visual reasoning. In particular, we propose to employ first-order logic to both describe a visual scene and reason about it. We then develop a differentiable inference machinery to probabilistically answer a question modeled via first-order logic in polynomial time. Finally, we use this framework to disentangle the visual and the reasoning aspects of visual question answering for the GQA task and study them separately. Given a visual scene over an object, we can describe it with quantified first-order logic formulas, where the uppercase variables refer to objects and predicates indicate object names, attributes, and relations. For example, the formula in this slide states that there's a man to the left of all objects in the scene. Interestingly, we can also use first-order logic to ask questions about the scene. For example, the same formula can encode the question, is there a man to the left of all objects in the scene? Then answering this question is probabilistically equivalent to computing the likelihood of the corresponding formula to be true. To compute the answer likelihood in polynomial time, we propose a recursive inference machinery, or as we call it, the Nabla FOL. Though differentiable, this formalism doesn't have any trainable parameters of its own. I leave the math details out here. Also, in our framework, the likelihood of the atomic predicates are calculated via neural networks, which we refer as the visual oracle. We can now use our framework to address important questions regarding the interactions between the visual and reasoning aspects of the visual reasoning tasks. One of such questions is how informative a given visual featureization is if we had to accomplish the tasks using mere logic. To be more concrete here, we look at the faster RCNN object featureization for the GQA task. To address this question, we built the base model as depicted in this slide. Now, because the base model reasoning here has no trainable parameter, the accuracy of it on the test data indirectly captures the amount of information in the featureization. So for example, in this case, using the faster RCNN featureization without any fancy reasoning capability beyond first-order logic, we can theoretically answer almost 52% of the questions in the GQA test data. Furthermore, if we replace the trained visual oracle in the base model with the golden GQA scene graphs, we observed that we could answer almost 96% of the questions in the GQA validation data. This upper limit not only shows that our first-order logic reasoning framework is sound, but also the GQA task is heavily vision-driven. The better visual perception, the better the question answering performance. Of course, achieving perfect perception with high confidence is challenging. But then the question is how much the reasoning process of a model can make up for its imperfect perception. To answer this question, we use the base model to partition the GQA test dataset into two hard and easy subsets based on whether the base model could answer the question or not. Now, if I have a candidate model M, the accuracy of M on the hard set tells me how much the reasoning process of M compensates for its imperfect perception, because the examples in the hard sets are the ones that do not have adequate visual signal to be answered only using first-order logic reasoning. Similarly, the error of M on the easy set tells me to what degree the reasoning process of M distorts the informative visual signals that would be otherwise suffice for logical reasoning to answer the question. Now, these statistics not only meaningful, but also comparable if measured for various models. For example, here we measured these statistics for two well-known MAC and LXMERT models from two different families of VQA models. As we can see, the gap between LXMERT and MAC becomes wider as we evaluate the reasoning condition on their perception using our proposed framework. This signifies the role of LXMERT reasoning model that can perhaps be attributed to extensive pre-training. This also signifies the importance of studying and comparing different models' reasoning in isolation from their perception, which we proposed a methodology for in this work. With this, I conclude this presentation and would be happy to answer your questions. Thank you.